In the last video, we introduced the idea that you can calculate different quantities for stars just by making measurements here on Earth and then using some relationships in those quantifiable units. Uh, in this video, we're going to extend upon that. And the irony here, when we're talking about brightness and luminosity, is you can see clearly it is darker outside than it was as I recorded the first video. So you can see the brightness changing throughout this lecture. Now, these are the 5 different quantities, for just a reminder for you that we started talking about at the beginning of this lesson. And 3 of these 5 we've already referred to and kind of gone through the calculation. The first of which is distance. Of course, distance isn't going to be measured directly. Instead, we typically will measure distance for now using arc seconds to find the angle at which the star is moving back and forth in the night sky. We have an equation relationship between arc seconds and parsecs, which is a unit of distance. Parsecs can be converted into light years. Light years can be converted into meters, which we'll use for our other equations. Brightness, we said, was in units of watts per square meter, is how bright, how much light is coming in for a given amount of area. And brightness very much depends on how far away you are from the object. And then luminosity is how much power a certain object is emitting. So the luminosity of a light bulb is 60 watts or 100 watts. The luminosity of a star is much, much larger. Now, we are going to talk about these other two and how they are related to the first 3. So we'll put them back down on the bottom here just to keep track of where we are at. To get to this next one, this idea of temperature, we need to use a relationship that we actually introduced last unit, and that is Wien's displacement law. This looked different last unit. In last unit, we saw this showing up as lambda max in meters is 2.90 times 10 to the negative third divided by the temperature in Kelvin. As a reminder for what this is actually representing, any body that is got a temperature that isn't 0 degrees Kelvin is emitting electromagnetic radiation. Right now, your body is, and the wavelength is that of infrared light. That's why you can see yourself glowing through an infrared camera. Um, but the actual wavelengths that are being emitted depend on the temperature uh, that the object is. And if you get hot enough, as we talked about last unit, you can start to glow in the visible part of the spectrum. And that's because as you heat up, the wavelength gets smaller and smaller. The wavelength getting smaller means that the frequency is getting higher, a higher energy. But the relationship here for that peak frequency, kind of this shape that's showing up, is this one here. Whether you present it like this or you present it like this, it's the same thing, just multiplying temperature on both sides. Something I want to point out here in the equation that's provided to you in this unit, MK is a unit, but it is not millikelvin like it looks like. Instead, it is actually meters times Kelvin to represent the wavelength in meters times the temperature in Kelvin. So if we go back to this example with Betelgeuse that we were using in the last video, we can actually measure based on the color of Betelgeuse what the maximum wavelength is of the light coming from that star. That star is emitting light with a peak wavelength of 828.6 nanometers. If we're going to use this equation, we must convert that wavelength into meters because this constant is in meters times Kelvin. So to convert that, we're just going to multiply it by 10 to the negative ninth because there are 10 to the negative ninth meters for every 1 nanometer. There's a billion nanometers per meter. So just make sure you go in the right direction. It should be a small number of meters. Notice that this isn't actually like official scientific notation because that first number isn't between 1 and 10, but that's fine. Is actually easier in some ways to understand because 10 to the negative ninth is very much related to that nanometers. So you can keep that same first number and then just tack on a different multiplier. So if I solve this equation then for t, just multiplying or actually dividing both sides by that maximum wavelength, and then I plug in that wavelength that we found before, we can calculate the exact temperature of Betelgeuse in degrees Kelvin. Now plugging that into my calculator, making sure that I'm using my exponent key to help me out, I find that that temperature is about 3,500 degrees Kelvin. So far, just from measurements that we've taken here on Earth, we can find the distance, the brightness, the luminosity, and the temperature of this star. We have one more to go. We're actually going to keep going and use all of that information that we've found so far to figure out how big the radius of this star is. To find that radius, first we need to review an equation that we've seen a form of in our last unit on energy production, and that is our equation for luminosity. The way we saw it before was actually an equation for power. We said that the power was equal to the emissivity times the Stefan-Boltzmann constant times the area times the temperature to the fourth. Here there's a couple slight differences. Instead of power, we're calling it luminosity, but again, it's in watts, it's the same thing. That the luminosity is represented with a capital L. Um, in our former equation, we saw that there was an E here in front of all of this for emissivity. In this case, the E is gone, but it's actually kind of still there. We're just assuming that it's 1. We're assuming black body radiation. So for simplification, when we're talking about stars, we just don't put the E in there. Sigma stands for the Stefan-Boltzmann constant. That will always be 5.67 times 10 to the negative 8th watts per square meter per Kelvin to the fourth. That will always be provided to you. You don't have to memorize that. A is the surface area of a sphere. Now, technically, it could be the surface area of anything, but in this case, if we're talking about a star, we're always going to be using a sphere to approximate the shape of that star. Now, you might remember, I used an analogy in our last unit of an orange. I peeled an orange and then saw that the surface area of that roughly spherical shape fit in perfectly to 4 times the area of the circles. So when you're calculating the surface area of a sphere, just remember it's 4 pi r squared versus a circle is just pi r squared. And then this last property here is the temperature, and that temperature must be in Kelvin. And essentially, when we're talking about stars, you'll very, very rarely see it in units of Celsius. It's typically always going to be measured in absolute units of Kelvin. Remember to raise that to the fourth power. That's kind of an odd relationship, something that we don't see very often, but that is really, really, really important if you want to get the correct answer. So back to our Betelgeuse example. Now that we know all of these other things, we know the luminosity, we know the temperature, we know the brightness and the distance as well, we can calculate the average radius. And you'll see in this equation that we know L and we know T, we know sigma because it's a constant, we don't know A. So we're going to plug in what we know and then just expand out for A. We could calculate for A and then solve for R separately, or you could just plug it in 4 pi r squared, use some algebra, and solve for R. Either way would work. In this case, we will find solving for R to be about 6.12 times 10 to the 11th. That is actually in units of meters in this case. I should have included meters on this slide. But we have now completed all 5 of these properties that we set out to find. And again, all we really used, the only values that we started with were the parallax angle between the Earth and different measurements. We found the brightness in watts per square meter, and then that peak wavelength. And from those 3 numbers, we found all of these other ones, ultimately leading us to the size of this star. Now, whether or not you find that as amazing as I do uh, is fine. But I think it's phenomenal that you can just look up at the night sky, take some measurements, and then figure out how big across that star is, something that's many, many light years away. You will find in your data booklet that you are given these equations, so you don't have to worry too much about memorizing them. The biggest thing that you need to factor in is that you need to know when to use them. So you have this luminosity equation, you have this brightness equation, and you also have over here this relationship with max wavelength and the temperature. So with these and with our constants and our conversion factors. We're going to go through one more example from beginning to end. So all together, we're going to do all of this for the star Sirius. This is the brightest star in our sky, and we can see that it has a parallax angle of about 0.379 arc seconds, an apparent brightness of 1.2 times 10 to the negative 7th watts per square meter, and a maximum wavelength of 292 nanometers. Um, we should be able to find all of these different values. The first one on this list is easy. Brightness is already given to us, so we're going to plug that in right there. The next one is already given to us as well. We just need to convert it into meters. So this nanometers into meters, basically just take that 292, multiply by 10 to the negative 9th, and we can get that value in meters. Next, we need to find the distance. The distance, the way we found it before, if you remember, is we take that parallax angle, and we plug it into this relationship that the distance in parsecs is 1 over the parallax angle in arc seconds. So 1 over 0.379 will give you 2.64 parsecs. Parsec is a weird unit, and is not one that we're going to be able to plug into our other equations down the line. So we're not going to plug that in as our distance. Instead, we're going to convert from parsecs into light years. Parsecs times 3.26 light years per parsec times 9.46 times 10 to the 15th meters for every light year will get us a total distance of 8.14 times 10 to the 16th meters. That's how far away Sirius is from Earth based on the parallax angle. Next, we want to find the luminosity. Luminosity is related to brightness and distance. So if we know the brightness, we can find the luminosity as long as we know how far away it is. Because until we know a distance, we don't know if it's a really, really luminous object that's far away or a dimmer object that's closer to us. So brightness alone isn't enough. We need distance as well. But now we have distance. So we can use this equation solved for luminosity. Um, the luminosity is brightness times 4 pi d squared, d being the distance that we calculated to the star. Plugging in what we know the brightness, we know this distance, make sure that you square it. We can find the luminosity. Luminosity is 9.98 times 10 to the 27th watts. Next, we want to find the temperature. The temperature here is related pretty much only to this maximum wavelength that we calculated here in meters before. And that relationship between the max wavelength and the temperature solved for temperature is just 2.90 times 10 to the negative third divided by that max wavelength. Plug that in, and you can find a temperature of 9,930 degrees Kelvin. And then we're left with the radius. To find the radius, we're going to use this equation that we just did, this luminosity equation. We weren't able to use this until we had the luminosity and the temperature. So all of these other pieces were kind of building up to this final measurement to be able to find the radius. If we plug in what we know, the luminosity, and we know the temperature, and we know Stefan Boltzmann's constant, or at least it will be provided to you if I'm ever going to ask you to do it. The only thing we don't know in that equation is r. Solving for r, we can find that the radius of Sirius, our closest star in the night sky, or the brightest star in the night sky, is 1.2 times 10 to the 9th meters. 1.2 billion meters across in radius. Now, this process is a beast. There's a lot going on there. But if you know generally how to flow through this and practice it a couple of times using this as a guide, uh, it's a pretty powerful thing that you can do. I will say that it won't always be in this exact order. You could actually start, like if you knew some information about the radius, you can go backwards, or you might not need to go all the way to the radius. And I might just ask, what's the luminosity? And that's as far as you need to go. But being able to do all of it is a really powerful thing and something that can be useful, even if you only need to know a part in a given problem.